the stability of the Atlantic Meridional Overturning circulation. And this was a collaborative effort with Wei Cheng, Sibren Drijfhout, Alexei Fedorov, Aishu Hu, Laura Jackson, Wei Lu, Elaine McDonough, Jennifer Macking, and Yashu Zhang. So this was a truly transatlantic effort. So the goals of our paper were to review the literature on the AMOC stability paradigm, to synthesize a current understanding of the stability of the AMOC, and to identify knowledge gaps and propose possible ways forward to address those gaps. And just to start with the end, these are the key points. We believe that it cannot be ruled out that the current or the future Atlantic Meridional Overturning circulation is in or close to a regime of multiple equilibria. Determining the proximity of the AMOC to stability thresholds is the main research challenge, and also that further research is needed to identify observable metrics that distinguish between an AMOC slowdown and a collapse. And this is a topic that I will not be talking about in too much detail today. So the AMOC stability paradigm is the idea that the Atlantic Meridional Overturning circulation could have more than one stable equilibrium. And what's more, that these transitions between these states can be triggered by either transient freshwater perturbations, for instance, some ice sheet melt event or so, but also by permanent changes in forcing, like permanent changes in the hydrological cycle, for instance. The paradigm emerged in the early 1980s when people started to realize that the climate has fluctuated pretty rapidly in the glacial period. Indicated here by this record from from one of the Greenland ice cores, showing the rapid downscaled ocean cycles, and then getting here into the current period of the Holocene of relatively stable climate. And this led to the suspicion that these rapid transitions were caused by changes in the overturning circulation. And this was an idea that was promoted, for instance, by Klaus Roth in his 1982 paper, but also by Wally Brooker and collaborators. And this is an influential paper from 1985. So Brooker et al. They cited a very obscure paper that had not received more than 3 or 4 citations in the 2.5 decades after its publication. And that, of course, is the now famous paper by Henry Stommel, the thermohaline convection with 2 stable regimes of flow. So Henry Stommel, he considered the density-driven flow, in which the density was controlled by both salinity and temperature. And he devised this simple 2-box model that we now interpret as having like a subpolar box and a lower latitude box, either equatorial or subtropical box or so. So he assigned the subpolar box a lower temperature than the equatorial box, but the salinity was controlled in 2 boxes, was controlled by an atmospheric freshwater flux, water vapor flux, like representative of the hydrological cycle. And dependent on the strength of this flux, the circulation in this model would either be thermally driven with downwelling in the northern box, or it would be salinity driven with downwelling in the equatorial box. But interestingly, due to nonlinearities in this system, there was a region in parameter space. So for certain strengths of this hydrological cycle, this freshwater transport, where both of these equilibria were stable. And this is an area that's called a region of multiple equilibria. So Weijer in his 1986 paper extended the Stommel box model with a southern box. He adhered to a strict equatorial symmetry, so he assumed that the southern box was as cold as the northern box, so TS and TN were the same, and they were both colder than the equatorial box, obviously. And he also imposed symmetric freshwater flux from the equatorial box to the high latitude boxes. And the basic symmetric circulation patterns in his model were exactly the same as in Stommel box model. So we have a thermally driven circulation with downwelling at the polar boxes. We have a salinity-driven circulation that is symmetric around the equator, but with downwelling in the equatorial box. But in addition to that, there were a bunch of asymmetric circulation patterns, the pole-to-pole circulation patterns. And one of them was the northern sinking pole-to-pole circulation, where the downwelling took place mostly in the northern box. and the exact symmetric circulation, reflective symmetry circulation of that is a southern pole-to-pole circulation, where the downwelling only took place in the southern box. So despite the fact that the model setup was totally equatorially symmetric, this model did allow asymmetric circulation patterns, like a spontaneous symmetry breaking that in this bifurcation diagram is indicated here by these pitchfork bifurcations. And this behavior was also found by Frank Bryan in his famous 1986 paper. It was a fully three-dimensional primitive equation model, double hemispheric, and it allowed like a symmetric circulation pattern as shown here, which is resembling this thermally driven circulation pattern with downwelling in both poles. But this circulation pattern became unstable to a southern sinking or a northern sinking circulation pattern. So this behavior that was found in this simple box model was directly, basically in the same year, also found in comprehensive primitive equation ocean circulation models. So I think the next step in the development of this AMOC stability paradigm was set by Ramstorff, Stefan Ramstorff, in his 1996 paper. He also considered a box model, also with northern and southern hemispheres, so a double hemispheric box model. But there are some very significant differences between his model and the LANL box model that makes this box model more similar to the Stommel box model. First of all, he did not allow any vertical motions here in the equatorial box, so this model only allowed pole-to-pole sinking circulations, northern sinking pole-to-pole, southern sinking pole-to-pole. But in addition to that, he also built in a symmetry from the get-go. So he assumed that the northern box was colder than the southern box. And you realize that if you have a northern sinking circulation pattern, that this fresh water flux really does not affect the strength of the overturning circulation. So the intra-basin fresh water flux does not affect the strength of the AMOC. And it is really this exchange between the Atlantic basin and the Southern Ocean, or the rest of the world ocean, if you will, that determines the strength and stability of the overturn. And as you see, this is kind of the equilibrium structure that you have in a box model like this, which resembles very strongly the Stommel box model. But rather than being intrahemispheric, so like just a North Atlantic model, Ramstorff's box model really expanded this to the basin scale, the scale of the entire North Atlantic in relation to the Southern Ocean or the rest of the world ocean. So another important step that he took, that he made a very direct link between the box model and the behavior in an ocean general circulation model. And he did that by calculating a hysteresis diagram using the so-called Hosing approach. And this is an approach that is now kind of a standard methodology to probe the stability of the AMOC in ocean models. So what he did, he applied the freshwater flux perturbation to the North Atlantic, and he slowly increased its amplitude, but with such a slow pace that it allowed the AMOC to adjust in a kind of a quasi-equilibrium way. So this is an example of the hysteresis diagram that he calculated. He started about here, and then he increased the freshwater flux very slowly, and you see that the AMOC gradually decreases until at some point the threshold is passed, and you see a rapid collapse of the AMOC. Then when he decreased the freshwater flux perturbation again, then the AMOC remained in off state for a while until another threshold was passed, after which the AMOC restarted very quickly, and it went back to the original state of strong overturning circulation. And the equilibrium structure that was implicit in this hysteresis diagram was, of course, very much consistent with the explicit equilibrium structure of the box model. However, explicitly determining the existence of multiple equilibria in ocean general circulation models is very difficult, and there are two reasons for that. First of all, there is a long adjustment time of the ocean to forcing perturbation. So if you would apply a freshwater perturbation in the North Atlantic, then it takes centuries or maybe millennia before the ocean reaches a new steady state. And so it's really hard to know if a state is a true equilibrium unless you're able to integrate for thousands of years. Also, these ocean general circulation models are unable to reach the unstable equilibria that are an inherent part of the equilibrium structure of the AMOC. So the development of implicit ocean models allowed us to directly calculate equilibria. And they do that by solving the system of equations in which the tendency term, the TDT terms are set to zero from the get-go. So it basically solves the stationary equations from the start. And this allows us also to follow equilibria using parameter continuation techniques. And that is an approach that Henk Dijkstra and his group at Utrecht University have promoted very diligently in the last couple of decades. To the best of our knowledge, this is the most complex model in which equilibria have been explicitly calculated using this implicit methodology. It's a 4-degree horizontal resolution. It's a 12 level. So it is a global ocean model, primitive equation ocean model, but it's very low resolution and obviously very viscous, very diffusive, as you can see here from the barotropic stream function that we're showing here. But it does show very clearly this same equilibrium structure that was found by Ramsdorff in the box model before that. So this is the branch of strong overturning circulation that's indicated here, the overturning stream function. This is the branch of collapsed overturning state, or in this case, it has the downwelling mostly in the Southern Ocean. And here we see a branch of unstable equilibria that connects these two branches. So we have limit points here and a limit point here that indicate the stability thresholds of the AMOC. Based on the literature, the equilibria of the AMOC are systematically found in a hierarchy of models. In the box models, of course, two-dimensional ocean models that are zonally averaged across the Atlantic, three-dimensional sector ocean models, global ocean models, eddy parameters climate models that are coupled to, in which the ocean models are coupled to an active atmosphere, eddy-permitting climate models. The only thing that, as far as we are aware, multiple equilibria have not been found yet is in eddy-resolving climate models. So this is something that in the next decade or so, our community probably should try to pursue, to find multiple equilibria, collapsed AMOC states, for instance, in eddy-resolving climate models. So we believe that this behavior of the multiple equilibria is fundamental to thermohaline ocean circulation, and we are very well aware of the critical ingredient, which is the salt-advection feedback. And the salt-advection feedback is an interaction between the overturning circulation that affects salt anomalies from the tropical North Atlantic to the downwelling regions in the subpolar North Atlantic, and these salt anomalies in turn strengthening the overturning circulation. So this is a positive feedback. And we believe there is observational support for that. It's just by looking at sea surface salinity distribution, and it's easy to realize that the salinities in the subpolar North Atlantic are much higher than any other subpolar basin in the world ocean. And it is pretty obvious that a large part of this high salinity is caused by the fact that we have an overturning circulation. And in addition to that, we know that the subpolar North Atlantic and the Nordic seas are areas of intense open ocean convection. And we think we know that this open ocean convection is critical for maintaining the strength of the Atlantic meridional overturning circulation. Then we've been wondering, so if the salt-advection feedback is responsible for multiple equilibria, and if it is an active dynamical element of the current, the present-day overturning circulation, are there other other feedbacks that impact the stability of the AMOC, and that could actually be more powerful, possibly, than the salt-advection feedback, making the salt-advection feedback moot. So we looked at several feedbacks, and the most obvious one is the heat advection feedback. So in the same process for which the salt-advection feedback works, the AMOC also accepts relatively warm water northward and increasing the buoyancy in the subpolar North Atlantic. So this is a negative stabilizing feedback. We also know from model experiments that the AMOC seems to pull the ITCC northward. So this tends to freshen the North Atlantic, and also leads to a negative stabilizing feedback. Then the Barron state transport also seems to be related to the strength of the AMOC, with a strong AMOC implying a stronger through flow and a stronger freshening of the North Atlantic, which also would be a negative stabilizing feedback. And we looked at a couple more feedbacks, for instance, related to the position of the westerlies in the North Atlantic. But based on our reading of the literature, we do not think that any of these feedbacks are really powerful enough to counteract, to make the self-advection feedback impotent. So then we also looked at paleoclimate. What does the paleo record tell us about AMOC stability? And this was a section that was written by Yashu Zhang and Alexei Fedorov. And there seems to be this classic picture of three modes of circulation of the AMOC during the history. So there's this warm on state, the strong overturning circulation that is characteristic of the current state, but also may have been states that were during the interstadials of these downside ocean cycles. Then there also is indications that there may have been a cold on state, in which may have been the basic state of overturning circulation during the glacial period. And this is a state in which the AMOC was not shut down. It was one in which the AMOC was weaker and maybe shallower, but it was still an active overturning state. And then there was this indication that the AMOC might have been shut off during certain times, and it's not quite clear if this really was an equilibrium state or just a transient state or something like that. But it's still an important state to consider. So based on our understanding of all this, we came up with a kind of a synthesis diagram in which we set out the kind of the classical hysteresis behavior as a function of the kind of a freshwater perturbation. And in this case, you can maybe think of this as a kind of a more or less permanent freshwater input from the Greenland ice sheet or something like that, or something more like the Heinrich sensor. So, but also a function then of the atmospheric carbon dioxide concentration. Present day high values, intermediate values during some past periods, and low carbon dioxide concentrations during the last glacial maximum level. So we believe then that for the current state here on this diagram is what we found in all these ocean models and the box models, in which we have a strong overturning state here. But we also may have like a collapse state. And again, we don't know if this is an equilibrium or not. In this case, so this is very speculative, but we put this on the line that currently we may have stable equilibrium of the overturning circulation. But again, this is speculative. So for the last glacial maximum, we might have a similar situation where we have an active overturning state and a collapse state. In this case, we plotted the collapse state to be behind the standard, the mean climate state at that point. But again, this is speculative. So in this case, we plotted the last glacial maximum as being monostable. We only had this cold on state, but it is very well possible that this collapse state, for instance, could have been triggered by rapid ice sheet disintegrations, for instance, associated with Heinrich sensor. So, and we believe that these warm on and the cold on states might be connected to each other through this branch of Equilibria as function of atmospheric carbon dioxide concentration. And there might be some hysteresis in this curve as well, as we plotted here. And a hysteresis behavior like this, or the kind of the limit points and the hysteresis behavior that might be associated with that, when you switch back the carbon dioxide concentrations from the left and the right. So you have rapid switches between these two modes of overturning circulation that could have been responsible for generating the downside ocean cycle. And of course, you add much more complexity when you then also consider the equilibrium structure in the freshwater perturbation plane. So to conclude, and got a couple more slides after this. So we think that it cannot be ruled out that the current or the future AMOC is in a regime or close to a regime of multiple equilibria. And these multiple equilibria have been robustly found in the hierarchy of models. We know the dynamics pretty well, the salt advection feedback, and we are not aware of any powerful counteracting feedbacks that could make this the salt advection feedback important. However, determining the proximity of the AMOC to the stability threshold is the main research challenge, and that is because the AMOC behavior is really sensitive to model details and biases. And to be honest, we have relatively low confidence in our ability to model the AMOC in climate models with any degree of accuracy. And to bring home that point, I'm showing here a figure from a paper that was just accepted by GRL, in which we looked at the AMOC in this current generation of climate models. This is the CMIP6 ensemble, and we're showing here the AMOC strength at 26 degrees north for the historical period. So the black line is the multi-model ensemble, and here the violet line here in the end are the rapid MOCA observation. And we see that the mean strength of the multi-model mean is very close to what rapid tells us it should be. But at the same time, we see an still incredible model spread. And if we are aware that the stability thresholds are really sensitive to the strength of the AMOC, then it's clear that it's kind of impossible to infer with any certainty, any knowledge about the location of the present day AMOC with respect to these stability thresholds. So really to wrap up here, the research challenges that we identified is to try to find multiple equilibria and adequate solving climate models. That has not been done yet, as far as we know, to the best of our knowledge. And then, of course, how close is the present day AMOC to stability thresholds? This is the main research challenge that we need to address as a community. What are the main feedbacks that compete with the salt advection feedback? I mean, we are aware of several, but there might still be some that we are not aware of, and there might be some that have not been quantified very well yet. So this is also something that could be a focus of our community in the next decade or so. And finally, and this is something that I did not address in this presentation, but that we did address in the paper, is how can we detect or predict an impending AMOC collapse? So can we distinguish between an AMOC collapsing or between AMOC gradually slowing down in a kind of a quasi-equilibrium response to external force and change? So this is my summary of our paper. So thank you for listening, and I'd be happy to take any questions.
Great. Thank you, Wilbert. So if you have any questions, don't forget to use the raise your hand button, which is located right next to your name in the participant list.
So has Henry raised his hand?
Yeah, sure. Thanks, Wilbert. So my reading of literature is that most of these hosing experiments have to do with hosing in the northern hemisphere. There's also been some modeling coming out recently of, quasi-coupling of Antarctic ice sheets with ocean models, which have shown that there's also, stability questions may be raising with southern hemisphere hosing, and that could affect both the AMOC and the lower cell, of course. So I was wondering if you had any comments on that.
We didn't really look at it. We really focused on the Atlantic basin as a whole, but you're definitely right that there's more ocean outside of the Atlantic, and that there's this strong indication from modeling in particular that there's an interaction between the strength of the North Atlantic overturning cell and the Antarctic bottom water cell. And that is definitely something that has not really been that still requires a lot of investigation, but it's definitely an interesting area that should receive much more interest than it has done so far, I believe.
I have raised my hand. Okay. I have a question for Wilbert. Is what is your thought about the last question you posed here? And I have a comment is responding to the previous question. Actually, Sidolf and Stauffer, they ran a simulation to put a 1/3 of freshwater falling from the Antarctic. What they found out is it will weaken. Okay, it will weaken the bottom water formation and strengthen the AMOC, or which is strengthen the deep water formation in the northern hemisphere. So basically, say it's a seesaw effect. If you have more freshwater input into southern oceans, it will strengthen the AMOC. If you reduce that freshwater input, it will strengthen the bottom cell, but weaken the upper cell.
So is it then due to the direct impact of this freshening on the dynamics of the northern cell, or is this due to the strengthening of the bottom water cell and then the interaction between the bottom water cell affecting the North Atlantic cell?
I think that's an interaction between the upper and lower cell. As Broker, they propose this seesaw-like change between northern and southern ocean. When the North Atlantic water formation is stronger, then the bottom water formation in the Antarctic becomes weaker. So that's the mechanism they propose for the millennium scale oscillation of the climate between northern and southern hemisphere. And Stauffer and Siddal, their experiment just demonstrated, yes, if there's a weakening or strengthening of Antarctic bottom water formation, it does affect the strength of the North Atlantic deep water formation.
Right.
Actually,
Great. Thanks for the clarification.
Some experiment using kinds of more close to the reality freshwater input in the Southern Ocean. I also see by weakening the bottom water formation, actually the AMOC is strengthened a little bit.
Right, right.
Yeah. Back to my question is what is your thought about the last question you proposed? How to can you go back to one slide?
Sure.
Yeah. This last question: how can we detect or predict an impeding AMOC collapse? Do you have any thought about on that?
Not really. So, but one thing that I would be interested in in this context, can we measure the salt advection feedback? Can we measure the amount of salt that is being transported northward through the Atlantic overturning circulation? And would that give any indication on whether or not there is being enough salt transported northward to maintain the overturning circulation, basically? That would be my thought. But I think people in the predictability community might have some ideas about that. I think that I saw Doug Smith online. I don't know if he has any thoughts on that, or maybe anybody else on the team.
Can you hear me? Yes, Swingodo is talking.
All right. So let's move to DDA. Trinidad, I think you had a question also.
Can you hear me?
No.
Kind of.
Yeah. Okay. Yeah. My question is kind of related with your comments on decadal prediction and within the research challenges that you highlight here. I have the feeling also that going beyond stable state and also having better research and insights on transient behavior. I mean, how many times will it take to have an AMOC collapse is maybe a question that has not been tackled a lot. And for instance, IPCC is stating that for the end of the century, it's unlikely or very unlikely, but there will be a collapse. Yeah, the question of time scale of a collapse is crucial, I think, also for society. And I was wondering what is your feeling, and do you have any insights on what can constrain this time scale? Because apparently it's pretty long, of the order of a century, but Do you have any insights if there are physical possibilities so that it can be faster?
So that's a bit quick. So you're asking about the timescale of on which a collapse could take place, and also you're referring to IPCC conclusion that the collapse of the AMOC is very unlikely. So let me start with that the first one first. Indeed, it looks like the present generation of climate models is relatively stable, and of course there's been a lot of discussion in the last couple of years in whether or not the low resolution climate models are biased stable, whether the AMOC is unrealistically stable in those models. And I think that is also still an outstanding question. So even if there's only a 10% chance of collapse, that would still be a very significant thing for us to understand. So I think it's important for us to understand the biases in these climate models and how those biases affect the stability. With respect to the timescale, it kind of may depend on what the mechanism of collapse is. I mean, if there's a change in the forcing that makes a certain equilibrium, if we go back to the dynamical systems approach, if that equilibrium just disappears to be equilibrium, then I think that the collapse may be pretty quick, maybe on the order of a couple of decades or so before it really when it really starts setting in, transitioning to another equilibrium. So if you have still two stable equilibria, and you have to apply a transient perturbation, basically, that it might take a little bit longer for the equilibrium to drift away from the other equilibrium, the stable one, basically. I'm not sure if that answered the question.
Yeah, it answers pretty well. Yeah. So for you, it's really related with the proximity to the threshold. Because my feeling was that when IPCC is stating that a collapse is very unlikely for the end of the century, I'm thinking it's mainly a question of timescale. It's not saying the collapse is unlikely. It's just saying for the end of the century. But if for the few simulations that are going longer, there's quite a few that do show a collapse, but the problem is just that it's not occurring in just a few decades, apparently in present generation models. But maybe it's also because the advection feedback is maybe quite weak because our model do not have a strong enough circulation. That's just a guess. Thank you.
Right. Yeah, that's certainly. Yeah. Thank you for that.
There's another part for this question is for current generation models, similar 6 models, and also similar 5 models. And most of the models, they do not include the ice sheet melting effect into the consideration. That contributes a big uncertainty for the future change of the event. And right now, we don't know exactly how strong the Greenland and ice sheet will respond to this moment. So if this response is really large, then the collapse of the AMOC can be much sooner than later.
There is literature on the topic, and you can have a look at IPCC's work dealing with that. It's not changing much in present day models.
Right now, we do not see any model really have an interactive dynamic acid model coupled with the climate model. And CESM2, we have some simulation with interactive acid model with the climate model. And the result is slightly different from the uncoupled acid model simulation. But it's still not strong enough to collapse the AMOC sooner than later. But still, and the acid is a frontier for our climate research community. We don't really understand it well enough to to definitely see what the simulated response will be the real response. It is possible the simulated response could be weaker than the real response because we have a lot of things we do not understand well enough for the edge.
Mm-hmm. Right. Are there any other questions? I can't see who raised their hand. Renell, come ahead.
Hi, Wilbert. Great talk. I was just wondering if there's consensus from the observational community as to what the observational estimates of parameters that we use to indicate stability. Whether all of them are saying we're in a state of multiple equilibria or not.
So that's a good question, and I didn't really touch on the FOV discussion. So that's kind of this discussion about whether the Atlantic or whether the overturning circulation imports or exports fresh water into the Atlantic across the southern boundary, basically 34 degrees south. And that's a pretty vigorous discussion in the last decade or so. With the idea being that if the AMOC imports fresh water, that the AMOC would be in a bistable state, and if it were to export fresh water, then it would be in a monostable state, or the other way around. So it's hard to do on the fly. But so there seems to be a discrepancy between models that seem to have a tendency to import fresh water compared to observations that seem to indicate that the AMOC exports fresh water from the Atlantic and imports. So that should be then indicative of a bistable regime, so collapsible state of possibility for the AMOC. And so that's kind of feeding into this discussion on whether the present-day climate models are overestimating the stability of the AMOC. And it seems to me, if you look at different estimates observational estimates of this fresh water flux, that they all seem to be indicating that the AMOC does seem to export fresh water, which would be mostly not consistent with what the present-day climate models say. Does it answer your question, more or less?
Yes, it does. Thank you. I always get it confused too, so don't feel bad.
Thank you.
I had, can you hear me?
Yes, we can.
Yes. Okay. So I had a question. Yes. So I had a question about. I know that there are multiple types of multiple variability timescales for the AMOC, and for the various convection spots, such as the Labrador Sea in the North Atlantic. That some we see in models, and different models can produce different timescales, and we can talk about 7 year, 20 years, and multi-decadal, and so forth. How do you see these variabilities from your framework of the hysteresis? And does the hysteresis need to be on centennial timescale? So I guess it's a question of timescales again, and how does your type of research connect to the multi-decadal variability of AMOC research?
Right. So part of this implicit modeling approach is that you can also calculate the stability. You can do an eigenmode analysis basically around a certain basic state, and what you see is that many modes of variability are stable, and they can indicate some of these decadal variability modes that you're talking about. So what happens when you reach a kind of a limit point is that one of the modes becomes unstable, and that is basically when you start to see these permanent transitions to other states, for instance. So the variability that you're talking about fits into this dynamical systems theory framework, but those modes are typically stable modes. They can be excited by maybe stochastic forcing or something like that, or in some cases they can become unstable oscillatory modes, in which case you have encountered like a Hopf bifurcation, as they call it. So the variability and the stability are very closely linked in this dynamical systems framework.
Thank you.
Does it answer your question?
Interesting. Thank you.
And we have two questions. Sorry about this. I was struggling with some audio problems on my end, but I think I have it sorted out. Two more questions, one from Caroline and one from Doug. And I think looking at the time, we can end there. So let's have Caroline's question first.
Thank you. Let's see. Here, yeah. Here. Hi, Wilbert. Good to see you, and thanks for the talk. I had a question about one of your final figures about the CMIP6 analysis. What stood out to me, but maybe yeah, thanks, if you could put it up again. Of course, we've seen the large spread before, that climate models are not very good at getting the average or the mean state correctly, but am I correct in saying that now we suddenly see a couple with huge variability that we didn't see before in CMIP5? And if so, do you have an explanation for that?
Sorry, can you repeat that question, please?
Yeah, I mean, if I think back on CMIP5, then I mean, the fact that the mean states, the mean AMOC strengths were, well, show a wide spread among models. That's not new, I would say. It's still a bit disappointing that we didn't get very far. But now I see, for example, that light brownish color is one which displays a huge variability, while others do not. Is that something we've seen before in CMIP5 and I just don't remember, or is this new in CMIP6?
Yeah, so just to clarify, what we're seeing here is the ensemble average per model. So some models have a very large ensemble, right? This one, for instance, 23 ensemble members, whereas the gray one, or the light brown one that you pointed out, has only one ensemble member. So there is a kind of a difference there. But I do think that even the CMIP5 models also had a significant range of variability, internal variability in the system. I think the GFDL model had a very persistent 25-year cycle in their overturning circulation. And so there have been a couple of studies that look at the internal variability of CMIP5 models. And I guess the conclusion also there is very little consistency from model to model about the internal variability of the AMOC also, and which is also very, very concerning, I suppose.
All right, now I was fooled by the one versus many ensemble members. Thanks for explaining that.
Right.
All right, Doug, thanks for being patient. Go ahead and ask your question.
Okay, yeah, thanks, Wilbert, for a nice talk. So I was just wondering about the role of the atmosphere in driving the AMOC and potentially in providing feedbacks. Do you have any comments on that?
Sure. So one of the feedbacks that I mentioned already was the ITCV feedback. The other one is the heat advection feedback that I also mentioned, where the AMOC transports heat from the lower latitudes to the subpolar latitudes. And one of the key elements there is that a lot of this heat is being lost to the atmosphere. So this signature, it disappears rather quickly, whereas the salinity signature of that advection process, it kind of retains, it's retained. But of course, if you transport warmer water northward, then the atmosphere adjusts, it takes up heat, and it loses some of its ability to take up more heat from the overturning circulation. So there is definitely a feedback there going on in terms of the air-sea heat fluxes. So some of the other things that we looked at, and that to be quite honest, I really don't understand in too much detail, but that were the impacts of the northward heat transport on the position of the westerlies, for instance, and strengthening of the subpolar gyre that can also have an effect on the strength of the AMOC. But as I said, I have not dived too deeply into that, so I'm not very confident in addressing those questions. Maybe if somebody else is of the co-authors is on there, I think Wilbert and Weijer has been looking at that in much more detail. Wilbert, do you want to comment on that if you're on the line?
Yeah, I'm online. So we've been a little bit looking to what seems to be the strongest atmospheric feedback in a lot of lower resolution models is that due to the shift in the IPCC, you get a salinification of the subtropical gyre. And then eventually the salinification over there spills over to the subpolar gyre, and then you kickstart somehow a convection again. And what we found in a higher resolution model is that MOV is much more negative, so much more stronger the salt advection feedback over the subtropical area, and then the shift, so the atmospheric feedback, so the shift in the IPCC and the salinification that results from that is weaker than the freshening due to the collapse or the weakening of the AMOC. So that feedback that exists in low resolution models does not exist in at least the latest HEDGEM 3 model, albeit maybe a slightly lower version than the very, very latest. Again, how model sensitive this is unclear, but we have the feeling that resolution is really helping here, because you get more salt transport by the AMOC by having stronger boundary currents and other processes that are typical for high resolution. But of course, we cannot draw firm conclusions on the basis of one model.
Yeah, thanks. I guess I was really thinking about the North Atlantic Oscillation as well, as one potential driver and feedback.
Yeah, but that is still quite weak, isn't it? So so we have the North Atlantic Oscillation that is driving the AMOC or the AMO, if you like, in many models. But if you want to have it really as a feedback in a coupled system on a collapse or slowdown of the AMOC, we need first that the weakening AMOC is evoking a certain NAO response, and that response is then again further weakening if it's a positive feedback, or dampening if it's a negative feedback, that initial tendency. And as you may know, this second kind of feedback or lagged feedback that some models have, and there are some indications that we have something like that in the observations, it's very, very weak. So yeah. So the response of the NAO to anything that is changing the ocean is very difficult to model. It also comes back to your signal to noise problem in the decadal prediction system, that you can sometimes predict the NAO, but you need quite a lot of members, and the prediction system seems to be better to predict the real world than itself. So so that all points down to a too-weak relation between the ocean and the atmosphere here in our coupled models. And Yeah, I don't think we have the answer on how to really improve that, isn't it?
Can I comment on that?
Yeah.
Yeah, just to mention that, yeah, you're definitely right in what you're saying, but I think Doug is thinking about, in reality, potentially stronger feedback. But even if it exists, I think this is a negative feedback. At least from the models that we know, studies from Guillaume Gastineau using different models has found that an increased AMOC leads to a negative NAO, which means that if the forcing of the NAO on the AMOC is as we think, this might be a negative feedback. So it might be stabilizing in a sense. Maybe that's what Doug has in mind.
But doesn't it also depend, DJ, on how important Labrador Z convection is versus Nordic Z convection? And yeah, and again with the Lozier paper, we're a bit puzzled whether the models are doing the correct thing or whether the results are possibly not representative because it's so short time period or whatever. But yeah, I would say it's not so clear. It's maybe a negative feedback, and it looks like in quite a few models, but it can also be due to this problem. So I would tend to be cautious, and it's very difficult to deduce some sort of feedback from first principles or observations if it's not really backed up by the models. And yeah, the models have quite a few problems here. So it could be, but I don't think we have we have a firm evidence here. We have been doing a little bit of Primavera analysis on low frequency patterns related to the AMV and the NAO, and there seems to be some indication that you get an NAO response that is lagging the AMV at higher resolution, but it's still very weak and not really significant. And the other way around is much more significant.
I agree with that.
Thanks for this discussion, guys. This is really helpful. Jenny, do we have to wrap up?
Yep, I don't see any more questions on the line, but I'm sure that if any do come up, we can contact Wilbert for them. So yeah, we should probably start wrapping up since it's almost a half hour past. So thank you everyone for joining us today, and thank you to Wilbert for presenting and having this great discussion with everyone. Our next AMOC webinar is going to be on July 16th. Laura Jackson from the UK Met Office will present on the paper, The Mean State and Variability of the North Atlantic Circulation, a Perspective from Ocean Reanalysis. So thank you again for everyone for joining.